Today, we'll finally be talking about angular momentum. Is pretty simple to understand. Just like linear momentum, which is sort of how much an object is carrying, and an object's momentum is conserved if force is equal to 0, mostly because force is equal to the change in momentum over time. Just like that, angular momentum is a measure of a very similar quantity, but instead of force being equal to 0, it's 0 when torque is equal to 0. So this is a very nice definition of angular momentum right now. But unlike our definition of regular momentum, it is incorrect. Why? Because MVR only holds when you're within a perfectly circular orbit. If you're not within a perfectly circular orbit, you suddenly have to add in the factor MVR sine theta, where theta is the angle between the momentum of the particle in rotation and the radial vector of the particle in rotation. Of course, in a circle, that's always a right angle, which makes sine theta 1, so you don't have to worry about it. But with something like an ellipse, especially an ellipse with high eccentricity, you can't say that the radial vector and the momentum vector are going to be perpendicular to one another all the time. So, angular momentum is a little bit more complicated. But it's not just that. We've still been talking about motion in a 2D plane. As soon as we extend an object's motion to 3D, say we have a spherical pendulum that is swinging around the unit sphere, that's another aspect of rotational motion that has to be encapsulated in our rotational quantities. Because, right now, this guy's a scalar, this guy's a scalar, this guy's a scalar. None of these guys are going to tell us what the plane of rotation is. Unlike these guys, or this guy, which is a vector, or this guy, which is also a vector, or this guy, which is also a vector, or this guy, which is also a vector. So as you can see, all of our rotational counterparts are scalars. And scalars are clearly inadequate to describe a system like this. So what we're going to do instead is we're going to associate a direction with them that's perpendicular to the plane of rotation. Even though it doesn't actually mean anything directly, it's the only way we can comfortably encapsulate what the plane of rotation actually is. Okay, so there we go. We've now defined L, angular momentum, as having a magnitude of MVR sine theta and being perpendicular to the plane of rotation. What is the plane of rotation? Well, it's the plane that's being shared by the momentum and the radial vectors. That's how you define it. But hold on a minute. So L is perpendicular to P, and it's perpendicular to R, and the magnitude of L is equal to PR sine theta. I'm pretty sure, hiding in plain sight, L is equal to P cross R. And there we go. That is angular momentum. So far, all of what we've been talking about applies to classical mechanics and classical mechanics only. But, you see, in quantum mechanics, we also have a definition for momentum. Well, it's a little bit more complicated than that, actually. So, momentum is more defined by an operator. But this operator is not momentum. It helps us find momentum. Because, to actually find the momentum of an object, you now need to solve for the eigenvalues of this operator. And you might say, eigenvalues, that's for matrices, not operators. Just wait. You have to solve this equation for both the eigenvalue and the eigenfunction. And the eigenvalues that solve it are what we actually call real momentum. So there we go. Now you might have noticed one more thing. This is a scalar. I've been lying to you. Well, actually, I haven't, because there is no momentum operator. There are only 3 momentum operators, one for each component. Because operators can't tell us about vectors, they can only tell us about scalars. There's no room for an eigenvector here, is there? So, now we know how to apply things to quantum mechanics. Why? Well, we have the momentum operator in our grasp. The momentum operator in specific, since I haven't told you yet, is IH bar partial x. Yes, notice that that does mean that if you really want to put P, momentum, as a whole vector, you can express it as IH bar nabla, or nabla is this guy. So there we go. We now have the momentum operator. And since we previously defined L as P cross R, hopefully that will allow us to get Lx, Ly, and Lz too. So we know through this that Lx is going to be ypz minus zpy. That is probably wrong. I have to check it. So actually, I'm supposed to be taking the determinant of this matrix, ijk, x, y, no, wrong order, px, py, pz, x, y, z. Yeah, it's zpy minus ypz. And you have ly is equal to xpz minus zpx. Lz is equal to ypx minus xpy. So things are going fairly well so far. That means that when transferring them to the quantum operators, plugging things in, Lx, the operator, is going to be factoring out the IH bar, z partial y minus y partial z. Ly is going to be IH bar x partial z minus z partial x. Lz is going to be IH bar y partial x minus x partial y. So there we go. We now have all 3 angular momentum operators. It was as simple as that. So we've successfully extended things to quantum mechanics. Now, if you remember the generalized uncertainty principle from a long time ago, it stated that if A and B are some observables, and we knew the value of the commutator of their corresponding operators, then the uncertainty with which we can measure both values has to be at least the absolute value of 1 over 2i, the commutator of the 2 operators. And of course, since multiplication is commutative, that should give you an intuitive reason for why the absolute values are there, since commutators are skew symmetric. If you reverse the order, it becomes negative. So there we go. We have that this is true. And therefore, when the commutator of two operators is 0, we call them compatible observables. So, if we have two compatible observables, then we can find an eigenfunction f that satisfies both. I.e., we can essentially find a reality where we can nail down the values of both A and B to 100% precision without any uncertainty. We can find a reality where the two values taking on some quantity do not contradict one another. So we can find f such that both is, I can switch Lx to Ly by just renaming this to x and renaming this to z, renaming this to z, and renaming this to x. So if you put every cyclic permutation means you switch every x to a y, every y to a z, and every z to an x. And through that, we can cycle through Lx, Ly, and Lz just fine. Which means that through cyclic permutation, we will be able to figure out all 6 possible commutators just by looking at the one, Lx, Ly. So let's do that. What is this commutator? Well, on the surface, it's just Lx, Ly minus Ly, Lx. We can't do anything with that. So instead, we need to apply it to a test function. Lx hat, Ly hat, f, which is equal to what? Lx hat, Ly hat, f minus Ly hat, Lx hat, f. Now, we're going to have to expand that even more. So, we already know that Lx and Ly come with that scalar multiplier of IH bar. So since it's being applied twice here and here, we're feeling free to factor out that IH bar squared. What's left is a monstrosity. We get z partial y of x partial z f minus z partial xf minus y partial z of the same exact thing. Gotta make sure that only took up half. Then we have plus or minus x partial z, z partial yf minus y partial zf plus z partial x of z partial yf y partial zf. So here it is, beautiful monstrosity. Put your shoes on. And so, what happens when we distribute out these derivatives? Well, we get, this is minus h bar squared. Over here, we have partial y partial zf. Now, there's a zx coefficient in front of it here, and if we look for it later on, we can see there's a minus xz coefficient in front of it there. Which means the whole thing has to go to 0. Then, if you look here, there's a minus z squared coefficient. So let's add partial y partial xf. There's a minus z squared coefficient here. And if we look for it later on, wait for it, partial x partial yf z times z is positive, so this also goes to 0. Then we have partial z squared f. The coefficient in front of it is minus yx. You wait a little bit. The other coefficient in front of it is minus x times minus y is positive xy. So this also goes to 0. Then we get a partial xf, but if you look everywhere else, it looks like there's not another partial xf, which means that this is probably standing by itself. We'll leave it be as plus y partial xf. Then we keep going. There's a partial yf, and it's also standing by itself, so we'll leave it be. Over there, you see the partial z partial yf, but we already covered our bases with that. You will also see the partial z squared f, but we already worked with that. Here you will see the partial x partial yf, but we already worked with that. The only thing left is the partial x partial zf, which I skipped over earlier. Oops. So you get plus partial x partial zf multiplied by, as you can see here, there's a minus zy coefficient. But earlier, there was a minus y times minus z is plus yz coefficient, which means this is also 0. So, of course, condensing everything down gives us minus h bar squared multiplied by y partial xf minus x partial yf. And so, if we exclude the f, that means the commutator of Lx and Ly was IH bar squared multiplied by y partial x minus x partial y. And that hopefully looks a little bit familiar, because if you recall, the LZ operator was just IH bar y partial x minus x partial y, which means factoring out the IH bar, well, rewriting it as IH bar times IH bar, this is just LZ, which means you get IH bar LZ. There we go. So we know that Lx and Ly give us IH bar LZ, and by cyclic permutation, that means Ly and LZ give us IH bar Lx, and LZ Lx give us IH bar Ly. And for the other three operators, they're simply the reversed versions of these. If the commutator of A and B is the negative of the commutator of B and A. So here we go. These are the commutators. One crucial thing you'll note, unless one of the components is equal to 0, which would by extension make one of the component operators is 0, which would by extension make that component of the angular momentum 0, none of the three are compatible. Which is very sad. When we plug things in to the uncertainty principle, we get that a standard deviation of our measurements with Lx multiplied by the standard deviation of our measurements with Ly will always be greater than or equal to h bar over 2. Remember, where was it? Generalized uncertainty principle. It was right there. Yes. It's 1 over 2i, the commutator of A and B. And of course, the commutator of A and B, or IH bar LZ, oh, there should be an LZ here. Sorry. So, we get something like this, which is unfortunately very, very sad. So we can't do anything about that. Can we find two quantities that are compatible? Well, the next optimal guess is to try the magnitude of L, or the norm. But you quickly realize that, what is this going to give you? The square root of Lx squared plus Ly squared plus Lz operators. Now, we've spent hundreds of years finding out what this thing means to no results. So imagine what would happen to no results. Fractional calculus. But imagine what would happen under a square root. All hell would break loose. So instead of doing that, our next best idea is to try L squared. At least that doesn't give us a nasty square root, and the squared terms are easy to define. They're just what happens when you apply an operator twice. So, is the norm squared of L compatible with any one of the components? Well, we have to test it. This is the right black. So, let's test it with Lx, and then we can use cyclic permutation once again in order to get Ly and Lz. So the commutator of L squared with Lx is what? Since L is a linear operator, like every single operator we're going to see, this gives us Lx squared Lx plus Ly squared Lx plus Lz squared Lx. Notice how I'm not drawing the hats, because that would be one too many hats. We get Lx cubed minus Lx cubed for this term, and so we get 0 here. Then what do we do about these other two? Let's first write out what these even mean. Consider that the commutator of a squared and b is equal to a squared b minus b squared a. Oh, sorry, why did I say b squared a? Ba squared. Now, it's tempting at first, even though you know it's not going to work, to rewrite this as maybe a times ab minus ba plus something. And then it hits you, this is just going to be a squared minus aba. So that's not going to work. What happens if you try to multiply a from the other side? Well, we get ab minus ba times a, which is aba minus ba squared. So that's not going to, hey, wait a minute. The problematic term on both sides is aba. So if we just add these two together because they have opposite side for the aba, we should just get what we want. A squared b minus ba squared. Which means, indeed, a times the commutator of a and b plus, not minus, the commutator of a and b times a, which means it's different from just writing the commutator of a and b. This is what the commutator of a squared and b is. So now we apply what we've learned to this. And we get Lx plus Lx plus Lx minus Lz. Now, notice the commutator of Lx and Ly is I(h bar Lz, which means that the commutator of Ly and Lx is just going to be that but negated. So we get Ly times minus I(h bar Lz, and the same thing is going to happen there. Ly and Lz do not commute, so we can't just swap the order and call it a day. but it won't make a difference in the end. I'm probably spoiling things. Plus minus IH bar LZLY plus commutator of LZLX is just IH bar LY. We already have it noted down. Minus IH bar LY LZ. Now notice that scalars always commute with operators. This term is minus IH bar LY LZ, and this term is minus, this should be a plus. Not sure why that's there. Notice that this term is minus IH bar LY LZ, and this term is plus IH bar LY LZ. Hence, they should cancel out. And notice similarly, this term is minus IH bar LZ LY, and this term is IH bar LZ LY. Hence, they should cancel out. So, at the end of the day, the commutator of the norm of L squared and Lx is 0. Which means that the norm of L squared and any of the three components by cyclic permutation, since that doesn't change the value of 0, are compatible. So that enables us to start talking about, is there any, no, I'm not using that space. That enables us to start talking about part 3. Finding eigenstates for both. And of course, that's going to start with finding eigenvalues. So how's that going to work? Well, first what we're going to do is we have to set up two equations. L squared f is equal to lambda 1f, and L some component of f, I'm going to pick, some component of L, I'm going to pick z for reasons you'll see in just a bit, is equal to lambda 2f. And now we have to solve for lambda 1 and lambda 2's possible values and f. How do we do this? Well, first, these are very messy things to work with. We're going to try and find the eigenvalues while totally dodging the subject of the eigenfunctions, just as a politician would. So, how do we start? Well, we're going to define ladder operators, L plus and L minus. One is Lx plus ILy. The other is Lx minus ILy. Now, you can probably see why I chose LZ. It's just very simple, and also works with the complex numbers analogy to keep Lx and Ly for the operators. And if we use both Lx and Ly here, and we used Lx or Ly over there, the commutator algebra would break down, and we don't want that. So, now we're going to be doing a little bit of funking around with commutators. Remember that when we were solving the time-independent Schrodinger equation, we used ladder operators. We started by assuming that we had one solution, and then, using a ladder, we multiplied that solution by an operator to go up one step and change the eigenvalue a bit. Then, we applied it again to keep going up steps. And of course, we could also use the ladder to go down steps and subtract from the eigenvalue over and over again. And one thing we noticed was that since having a negative energy makes no sense, or having a negative wave function makes no sense, we have to hit, having a negative energy makes no sense, we have to hit a floor eventually with how low the eigenvalues can go. At some point, it has to go from positive to 0. And then as soon as it hits 0, nothing past that point is applicable to the physical world because all of the wave functions are going to be 0, non-normalizable. That's like our signal that everything that was useful to us has just finished. So there has to be a bottom at some point, and the rung right before that, minus n, has to be 0, where n is, how high or how low the eigenvalue goes per step. Now, we're going to be doing something very similar with our ladder. But instead of having just a bottom, there's going to be both a top and a bottom. We'll see why in just a moment. So, what happens if we have a solution f naught, and to go with it, lambda 1 and lambda 2? Let's say we've already found these. Finding them is for another time. If we've already found these, then let's say L squared f naught is equal to lambda 1 f naught. This is confirmed 100% true. This is just proof by assumption. Now, I want you to prove, well, not you, I want to prove that the same thing works with L plus and a possibly different eigenvalue. What happens when we do this? Well, consider that L plus is a linear combo of Lx and Ly, which means that, this commutes with L squared, since L is a linear operator. The commutator of L squared and L plus is just the commutator of L squared and Lx plus I times the commutator of L squared and Ly. This goes to 0. That also goes to 0. Everybody's happy. Which means that these two are perfectly fine to be switched. And an operator always commutes with a scalar. Which means that indeed, once we remove the L plus from both sides, L squared f naught is equal to C f naught for some C. In fact, we already knew this was true for lambda 1. So, since this is equal to lambda 1 f naught on the side, that forces lambda 1 is equal to C. So the eigenvalue for this equation doesn't even change if we go up and down the ladder. But as you've probably foreseen, since LZ does not commute with L plus or L minus, and hold up, yeah, might be worth showing that the situation is the same for L plus or L minus. It doesn't matter either way since both commute. So here, no matter if it's L plus or L minus, these two guys are going to commute. So this is going to be plus, plus, minus. So this is not equal to 0, as you've probably foreseen. What is it going to be equal to? How do we solve that equation? Well, let's write it out. We get LZ f naught is equal to lambda 2 f naught. We already know this is 100% true. That's another proof by assumption. Now, we want to know if LZ L plus minus f naught is equal to C L plus minus f naught for some C. Does this work? Well, these two don't commute exactly, but here's what we can do. I'm going to write L plus minus LZF naught. Boom. It's done. Nah, I'm just kidding. This obviously makes no sense because they don't commute. So what I'm going to do is immediately reverse my mistake by subtracting L plus minus LZF naught. and then I'm going to add back the original thing, and everybody is going to be happy. Now, we can condense this into just, watch carefully here, the commutator of LZ and L plus minus. Sorry, my handwriting is bad because it's at an awkward angle. Is equal to, and what I'm going to do now, a little bit of foreshadowing, is just reverse the order of these two, which of course operators always commute with scalars. Alright, so there we go. We have this. Now, what's the commutator of LZ and L plus minus? Well, LZ and L plus minus's commutator, we already have it here. So this is equal to what? Well, it's equal to the commutator of LZ and LX plus minus I times the commutator of LZ and LY. Now, we already knew the values of these from a long time ago, where we said that the commutator of LZ with LX is IH bar LY. And we said that the commutator of LZ and LY is minus IH bar LX. Which means that this becomes I times minus I, which is just 1. And so this is H bar LX. And so, hey, wait a minute. This is just H bar multiplied by L plus minus. We got lucky. Which means that, plugging back in here, this becomes L plus minus LZF naught plus H bar L plus minus F naught. And of course, since operators always commute with scalars, I think this is like the 5th time I've said that today. We get L plus minus H bar F naught is equal to L plus minus CF naught. Yeah, that seems about right. So things are going well so far. Now you remove the L plus minus from both sides, and you get LZF naught plus H bar F naught should be equal to CF naught. Hold up a minute, buddy. Hold up a minute, Buster. Hold on. Oh, yep, that's not right. Okay, so notice that I made a mistake here. Whether it was to trip you up or I did it intentionally, who knows. So, if we multiply, what happens if we have IH bar LY plus H bar LX? Then I'm correct. This is H bar L plus. But, you warned, IH bar LY minus H bar LX is not equal to H bar L minus. Because I'm dumb. This is equal to minus H bar L minus. So, in actuality, I should have put this down as plus minus H bar L plus minus. My bad. So now, this is equal to LH bar plus minus, and we get that since we already assumed LZF naught is lambda 2F naught, lambda 2F naught plus minus H bar F naught is equal to CF naught. Or in other words, if you divide by F naught, C is equal to lambda 2 plus minus H bar. So now we know why they're actually called the raising and lowering operators, because they raise and lower this eigenvalue specifically. But wait, now we know why there must be a top rung and a bottom. Because there's one thing that doesn't make any sense. Lambda 1 has to stay fixed, but lambda 2, so lambda 1, the magnitude squared, can stay fixed, but lambda 2 can go on infinitely in either direction. So there has to be a limit, because there is absolutely no way the lambda 2 squared can be greater than lambda 1. There is absolutely no way one component's magnitude is greater than the entire vector's magnitude. That breaks all known laws of vector calculus, which means that, of course, there has to be both a bottom rung before the critical line of minus LZ is less than or equal to minus L, and there also has to be a top rung right beneath the top line. LZ is greater than or equal to L. So, in between, we actually have a ladder where you can go up one step by applying L plus, and your eigenvalue will be raised by H bar. Or you can go down a step and shrink your eigenvalue by H bar, just like this eigenvalue, except it's a finite ladder. So just like this ladder, except it's a finite ladder. So you could, I don't know, put it in your house or something. So now you know about the ladder of eigenvalues. But that doesn't actually tell us about what the eigenvalues could possibly be. They could be 1 plus H bar, 1 plus 2 H bar, 1 plus 3 H bar. They could be a pi plus H bar, pi plus 2 H bar. They could be, I don't know, the Euler-Mascheroni constant minus H bar, the Euler-Mascheroni constant plus H bar. Nobody knows. We need to actually concretely figure out that base value. And how do we do that? Well, we take advantage of the top and bottom rungs. So, since there's a top rung, there has to be a top function, ft, such that L plus ft has to be equal to 0. And just like that, there has to be an fb, such that L minus fb is equal to 0. Now let me show you something. L plus and L minus are tricky operators, because it kind of looks like one is the conjugate of the other. But that is actually untrue. Yes, they are technically the conjugates of one another if Lx and Ly were scalars, but Lx and Ly are not scalars. So instead, what happens when we multiply L plus and L minus together? Well, we get Lx plus ILy times Lx minus ILy, which distributes to become Lx squared minus minus ILXLy, and then plus ILYLX. Normally these two would cancel out, but we're dealing with operators, not scalars, plus Ly squared. Normally, we would expect it to be just these two terms, but now it's all four of them. And look here. This right here is just I times the commutator of Ly and Lx. And that is just minus I bar Lz, which means that L plus L minus is equal to Lx squared plus Ly squared plus H bar Lz. Now, that means something nice. L squared can be expressed as Lx squared plus Ly squared plus Le squared, which I wanted to abbreviate this, which is why I was going into the L plus L minus rabbit hole in the first place. Now we know that this is L plus L minus minus H bar Lz plus Lz squared. Great. Now, L squared FB is equal to lambda FB for some lambda. Let's call it lambda B. So, oh no, shouldn't be that. LZ FB has to be equal to lambda FB for some bottom B. And now consider that L squared FB has to be equal to the default eigenvalue, lambda FB. And also consider that there's a top rung, and you have to work around that as well. So what does this give you? An eventuality. Well, when we expand this guy out, we get L plus L minus FB. There's nothing under FB, which means that term goes to 0, minus H bar LZFB plus LZ squared FB. This is all that we're left with. And of course, this is minus H bar lambda FB, and this guy right here is equal to, sorry, this would be lambda B, and this guy right here should be lambda B squared FB. That is, L squared, or lambda, should be equal to minus H bar lambda B plus lambda B squared. This should be it. And I mean, this looks pretty uncanny, right? The only way this makes any sort of sense is if lambda B is some multiple of H bar. So let's just assume that for a second. What happens? Well, we get lambda is equal to minus n H bar squared plus n squared H bar squared. And now consider that lambda itself, since lambda B is nh bar, lambda itself has to be lambda B plus some amount. Let's call it mh bar, which means it has to be m plus n h bar. Oh, sorry. So when you have this weight on your shoulders, it means the only possible way through is for n to be an integer and for n squared and n to cancel out with one another. So that's it. N is an integer or half integer. One more piece of evidence backing this up is that since we're getting from the bottom all the way to the top in an integer number of steps, n, that means that this eigenvalue has to be minus n over 2h bar. This eigenvalue has to be n over 2h bar. And one more thing to reinforce that, you might ask, well, don't we pass over 0, which means everything after that gets crossed off? Well, no. Perfectly fine, you can pass from minus 1/2 h bar to 1/2 h bar without ever touching 0. So there we go. We now know what all the eigenvalues are. All the possible eigenvalues are just some integer h bar over 2. So that is the end to part 3. Now it's time for part 4. We know the eigenvalues. Now it's time to find the eigenfunctions. So I want to start this with a callback to when I said P is basically just I bar nabla. So then that means P cross R, which is angular momentum, is just I bar nabla cross R. Now what I'm going to do is convert to spherical coordinates, which sounds like a dumb decision, but we don't have many other choices. So r becomes r the scalar times r hat, the unit vector. Expanding this out gives us ih bar multiplied by, what is Nabla in spherical coordinates? Well, we have r hat cross r hat partial r plus r hat cross theta hat divided by r partial theta plus r hat cross phi hat over r sine theta partial phi. So this is what we're now working with. So a vector cross itself, we isolate the scalar, it has nothing to do with the cross product, is equal to 0. So this term disappears. R cross theta is phi, and these two disappear. These two also disappear. R cross phi is minus theta. Which means that we're left with ih bar multiplied by phi hat partial theta minus theta hat cosecant theta partial phi. Now, we're doing pretty good so far. We want to convert all the way back to Cartesian coordinates. Not these guys, obviously, they're too far gone. Just partial theta and partial phi. Why? Because we used to have Lx, Ly, Lz. Those are nice. We don't want to convert to Lr, L theta, L phi. Those are probably gross. So instead, we're going to see what we can do if we express Lx, Ly, and Z themselves in terms of Lr, L theta, and L phi. So what if we do? Well, consider spherical coordinates. In spherical coordinates, if we have a point over here, r is this, of course, and this is what I got confused with a lot of the time. Theta is the angle lurking in the xy plane, while phi is the angle that takes you out of it. So that's the very important distinction between theta and phi. So now what happens if you convert to Cartesian coordinates? Well, you can now say that partial theta is in effect like saying sine theta partial x cos theta partial y. But these guys have to be converted to Cartesian coordinates because we used to have Lx, Ly, and Lz. They were super nice. And we don't want to convert to Lr, L theta, L phi. Those are probably really nasty. So instead, we're just going to try to keep everything in spherical coordinates, but split it into 3 components. Cartesian, if you know what I mean. So this guy decomposes into minus sine phi minus cos phi 0. And this guy, meanwhile, decomposes into cos theta cosine phi. Sorry for the awkward handwriting. Let me think. Sine theta, theta sine phi, cosine phi, sine phi. Simplifying this down gives us ih bar phi hat partial theta minus theta hat cosecant theta partial phi. Now, I want to convert these guys back to Cartesian coordinates because we used to have Lx, Ly, and Lz. They were so nice. And I don't want to convert to Lr, L theta, and L phi. They're probably nasty. So what we're instead going to do is, if you know what I mean, split it up into 3 Cartesian coordinates, but keep everything in spherical. So this guy becomes minus sine phi cosine phi is 0. And that guy becomes cosine theta cosine phi, cosine theta, sine phi, minus sine theta. And now, we also multiply this by the cosecant theta, which actually gives us cotan theta, cosine phi, cotan theta, sine phi, minus 1. And so, now we can start working. Now we can break this up into 3 components. Lx, which is equal to what? There's a minus sine phi over there. Then, there's a partial theta over there as well. Minus cotan theta cosine phi. I'm not missing anything, no. Multiplied by partial phi. Ly is equal to what? There's a cosine phi there, partial theta, minus, well, there's a cotan theta sine phi over there, partial phi. And LZ is nice. We just get what? There's no LZ component here, and the only one here is, I forgot the IH bar. We'll just add it in. LZ is just IH minus IH bar, remember the minus 1 here, partial phi. So there we go. These are the 3 operators that we're going to be working with. We also want the ladder operators. So let's express those really quickly. We get L plus minus is equal to what? Well, Lx plus minus Ily, which is IH bar multiplied by minus sine phi plus minus I cosine phi partial theta minus cotan theta times cosine phi plus minus I sine phi multiplied by partial phi. Now, notice that by Euler's theorem, this guy is just e to the plus minus I phi. And what is this guy? Well, he's a little bit more dangerous. If you rearrange this, this is actually plus minus I cosine phi minus sine phi. And what does that net you with positive or negative? Well, you have to do some careful case-by-case analysis. With the positive, I cosine phi minus sine phi, what happens is this is equal to I times cosine phi plus I sine phi. Which means that the plus version of this is I e to the I phi. Now, what is the minus version? Well, that's when you write this. And that is also dangerous because this is, well, also, it's minus I times cosine phi plus I sine phi. Which means that it's minus I e to the I phi. There we go. It always helps to be careful. Which means that in the end, it was just plus minus I e to the I phi. So this was IH bar times plus minus I e to the I phi multiplied by partial theta minus, this is e to the I phi, e to the plus minus I phi. That should be plus minus 2. Minus e to the plus minus I phi multiplied by cotan theta partial phi. So what do you get in the end? Well, you distribute this guy inside, and eventually you get plus minus h bar e to the plus minus I phi multiplied by what's inside, partial theta plus minus, or yeah, it was plus minus cotan theta, I cotan theta partial phi. So this is, sorry, I should probably extend the box, L plus minus. All it's left to do is solve it with bloody hands. So we start with equation 1. LZF is equal to, LZF is equal to lambda f for some lambda. Well, actually, we know by now that it's, let's call it, I don't know, L times L plus 1 because it looks cool. H bar over 2. So, and this would be an F as well. So now, LZ is what? IH bar. You know what? Let's just write MH bar. This gives us LZF is just IH bar partial phi, which means that partial phi f is actually equal to minus IMF. And that implies that f is factorizable into some function of theta and e to the minus IM phi. What else could give this? So there we go. We already have f factored into separation of variables automatically. Quantum mechanics loves us. It already knows what we're going to do. Squared f is equal to mh bar f. Things get just slightly more complicated. We're going to take a page out of the book of whatever was here prior. Where was it? Where was it? I know you're there somewhere. Where is it? Is it not here? Oh, I guess I can also try. Wow, where the hell did it go? Well, we already know that L squared is equal to L plus L minus H bar LZ plus LZ squared. Expanding on that, because if we did it with the original definitions, we'd have to deal with Lx and Ly, which are the nastiest operators, compared to Lz, which is nothing but a measly derivative. There was a minus sign on Lz this whole time? Minus I bar, so this is IMF and this is IM. Sorry. So now what happens here? Well, we get L plus L minus F minus H bar LZF plus LZ squared F is equal to MH bar F. So, just to be blunt, things get bad. Very bad. Like, incredibly bad. So what happens now? This gets us to L plus is H bar e to the I phi multiplied by partial theta plus I cotan theta partial phi. L minus f is partial theta f minus I cotan theta partial phi f. Oh, and there should be h bar e to the minus I phi in between. It's tempting to cancel these two out, but remember, the e to the minus I phi is being acted on by this operator. They don't commute that simply. So we get minus h bar, and the rest of this is cookie cutting essentially compared to whatever the hell this is. We get minus h bar multiplied by minus IH bar derivatives, because there's not much else we can do. Oh, there is one thing we can do. There's an h bar here and an h bar there, and double h bar here, an h bar squared there, and an h bar squared there, which means we can actually randomly cancel out a whole lot. This is plus I, minus I squared is minus 1. Okay. Now it is time to keep working. I'm sorry. So you get e to the I phi. And what happens when you distribute this? Well, first thing we're going to do is factor f into theta of theta e to the I m phi. So what you get here is e to the I phi multiplied by partial theta plus I cotan theta partial phi e to the minus I phi. Partial theta f is going to be theta prime e to the I m phi minus I cotan theta. Partial phi f is going to be I m, which is going to give us plus m cotan theta. Theta to the e I m theta phi. Now we can distribute this guy in here, which gives us minus 1, m minus 1 here, and an m minus 1 there. Then you have plus I, partial phi of f is I, well, it's going to give us minus m multiplied by theta e to the I m phi, and then minus partial phi squared is going to give us, well, this is going to come down twice, so minus m squared multiplied by, oh, and this is actually going to become a plus because of the I squared, theta e to the I m phi is equal to m theta e to the I m phi. Now, we can't exactly cancel out the I m phi yet. It's going to take a little bit more time. Multiplied by, when you distribute this, you get, I'm going to bring up the other blackboard. No. Yeah, I can bring it up as long as I make it very high. Alright. So this becomes e to the I phi multiplied by, when distributing this, you get theta double prime e to the I m minus 1 phi plus, here we are going to have to use the product rule, m theta prime cotan theta e to the I m minus 1 phi, and then minus m cosecant squared theta, theta cotan theta, oh no, not cotan, e to the I m minus 1 phi. Okay. And then we have to distribute the partial phi derivative. So we get plus I multiplied by theta prime cotan theta e to the, well, this comes down and becomes m minus 1 e to the I m minus 1 phi. and then plus Im cotan squared theta Im cotangent squared theta partial phi e to the Im minus 1, which makes this minus m times m minus 1. Cotan squared theta e to the Im minus 1 phi minus m theta e to the Im phi plus m squared theta e to Im phi is equal to m theta e to the Im phi. Now, we can actually distribute the e to the I theta all the way over here into this product, which makes this Im phi, this also Im phi, this is also Im phi, this is also Im phi, this is also Im phi, this is, oh, we already changed that. Okay. Now, we can actually cancel out the e to the Im phi's. We can finally get the gratification that we've been waiting minutes to get. I love instant gratification. Theta prime cotan theta minus m cosecant squared theta plus I theta prime cotan theta minus m times m minus 1 cotan squared theta minus m theta plus m squared theta is equal to m theta. I want to comment on the remarkable fact that this thing, well, when you multiply it by sine squared theta, is exactly the equation solved by the spherical harmonic. This guy from when we were solving the radial Schrodinger equation. Not just that, the spherical harmonic's phi component is e to the Im phi. That's it. The solution all this time was this thing. Y Lm theta phi. That is the eigenfunction that solves the angular momentum equation. That's it for today, finding the eigenvalues and eigenvectors of angular momentum. Tomorrow, we're going to be talking about spin, which is very similar to angular momentum,